So this is a closing video to week 6, and I want to say a few things that I would have said at the physical lectures if we had had them. And this is mainly about efficiency in the context of imprecision or probability related to primality tests. So we've talked about is-prime before. So is-prime is a way of testing that a number is a prime. The way that it's done in Maple, you can be sure that if you feed is-prime a number and it says this is not a prime, then you can be certain that it's not a prime. It will not tell you a number that factors your number, and that's part of the deal. However, if it tells you that a number is a prime, you can actually not be sure of that. It will, essentially what this means is that this number has withstood a lot of tests that would reveal that it was not a prime, and then Maple has sort of stopped testing. Right? So it means that with a very high probability, the number that you're seeing is in fact a prime, but not with mathematical certainty. And I want to say a few words about how this can be, and also what we can do about it. So, starting very sort of naively, of course, if you want to test that a number which is not too big is a prime, then what you can just go through is all the numbers from 2 to the square root of the number and see if they divide, right? Because if there's a, if you want to see if it's a prime, you have to find out if there's a factor between 2 and n minus 1 of it. But of course, if you can find a factor x, then n over x is also a factor, and one of these numbers is going to be less than or equal to the square root of n. So you can get by with going only to the square root. And so this is the easy way you can see if a number is a prime. And of course, this is something that works very well, but it takes a long time if you have a large number. And I'm going to run through some random numbers between 10 to the k and 10 to the k plus 1 and time them. And of course, my algorithm will, the time consumption with my algorithm is going to be quite different in different settings, because if I have a number, for instance, that is even, then the very first time I try to divide 2, see if 2 divides, then of course if 2 does divide and it's not 2, then I know straight away that this is not a prime. Right? So what takes a long time is a situation where you do have a prime and you have to go all the way up to the square root, or if you're sort of unlucky and the number is composite, but with 2 numbers that are very close to the square root. So let me just set this running because I know it takes a little bit of time. So what happens here is that, first of all, I've taken the average over 500 tests of primality with my naive algorithm, and you can see, of course, that it grows very quickly. But of course, it's actually not so fast, in the sense that I'm feeding numbers that are getting bigger and bigger, right? So the input in my algorithm is k, but I'm using k to take 10 to the k, and that essentially decides the number of digits in the numbers that I'm asking for are primes or not. So the input is growing exponentially, so of course it's not so surprising that the computing time is also exponential, and actually we're having the square root help us here in this computation. But still, you can see that if I have very big numbers, and also the average time is less than 1/100th of a second, so that's not so bad, even up to 9-digit numbers. But of course, the point here is that if I want to look at big numbers, like 100 digits, something like that, this is just going to be too slow. So while I was speaking, I also did the same for is-prime. And if I plot the time consumption here, you can see that it's sort of, again, it's a lot smaller than it was before. But the point here is that, and it varies quite a lot, but the point here is that it's almost constant. Right? So even though I have, in this case, I've run like 50 digits numbers, it doesn't seem to take a lot more time than it did for 10-digit numbers. And this, of course, tells you that the algorithm I'm using here is nothing like the one that I showed you. It doesn't go through all these numbers up to, for instance, 10 to the 25, which is the square root of 10 to the 50. So, that's not what it's doing here. It's doing something completely different. And of course, you can sort of see in this plot where I did, the blue is the naive version, and the red one is the clever version built into is-prime. So you can sort of see why I want to do it. It's a lot faster, But of course, it comes with this little downside that you cannot actually be completely mathematically certain that the answer is correct. Let me give you a brief idea of how this works, and let's go through one of the most sort of basic tests for primality that is due to Fermat. Fermat proved, this is called Fermat's little theorem. It's fairly easy to prove, actually. So if you have a prime, then Fermat says that if you have a number that is, say, between 2 and the prime minus 1, then if you take that, this is what I'm calling A, then if I take A and take the p minus first power of this, this has to be 1 modulo p. Right, so Fermat's theorem is a theorem about primes. So it says that if you have a prime, then you have a certain behavior. And it doesn't really say anything about what happens if you use this same, if you do the same computation with something that's not a prime. And this, of course, is the weakness of the primality test. So let me show you how this works. So I'm running through the numbers between 1100 and 1200, and I'm using my prime test. And the way the prime test works is that I take a random number. That's my A. I compute A to the n minus first, and I take the remainder modulo n. And then, as you can see, sometimes I get a 1 out, and sometimes I get something out which is not a 1. Right? And what this means is that if you see a 1 here, this is a number that is probably a prime, or at least I could say that it has a certain feature in common with primes, namely that if I take this A and I make this computation, I get the number 1 out. But if I have a number like the first one here, which is 200, which is not 1, this shows with certainty that what I have here is not a prime. Of course, the number that I'm using my test on is 1100, which is very clearly not a prime. So, so what happens here is, of course, not very useful. But the point is that this is really an efficient way of sort of sorting the numbers in a very basic way into numbers that are clearly not primes, and then numbers that with some probability are in fact primes. So using is prime, and here, small numbers like this is prime has been tested, so we know for sure that this is correct. So if I run my test on these numbers, you can see I always get 1s out. But if I select the numbers that I get out of that will sort of pass my test, so the numbers that actually give me a 1 out, you'll see that I get some false positives, right? 1105 and 1183. These are numbers that pass the test, but they are actually not primes. And then, of course, I could try to do this again. I do this experiment once more. And then what happens this time is that I get some different numbers out. 1183 didn't make the test the second time, and so I get 1105 out. And actually, 1105, of course, this is clearly not a prime. It's divisible by 5, as you can see. It's 5 times 13 like times 17. This is a so-called Carmichael number that has the property that actually whenever you feed it an A, which is not, mutually prime with this number here, then you'll get a 1 out. So, I mean, you can still use my test to see that this is not a prime, but the way it works is that the only way that this test can work is that if you're lucky and you find a number that has a factor in common with 1105. So for instance, if it's divisible by 5, then when you do this test, you'll get a number out which is also divisible by 5. So you can see, get this once in a while. This number here probably is divisible by 13. So you can do this test and it will work for Carmichael numbers as well. It's known that there are infinitely many Carmichael numbers, so this is a serious problem. But the probability of this working is a lot smaller than it is for other kinds of numbers. So it's sort of still working, but it's not as efficient as it is for non-Carmichael numbers. And in fact, isPrime will do all kinds of other advanced things, not just this test. But at the end of the day, what you're getting out is really not a result saying that this is a prime. What it says is that this is a number that has been tested for being composite many, many times, and every time it's failed. Right? So what this means is that you cannot know for sure whether or not this was actually a prime. And in most cases, this is fine, right? But for experiments, usually that's perfect. But sometimes we want to know for sure. We encountered an instance of this when we talked about the Goldbach conjecture, or actually the ternary Goldbach conjecture, where we needed to know that there were primes with a certain distance. I believe it was primes that had a mutual distance that was less than 10 to the 15, all the way up to 10 to the 18. Right? So we're talking numbers that are not super big, right? They're like 18 digits or something like that. But we want to know for sure this time that they are primes. And this is not really a place where you can use is prime, right? Because is prime will just tell you that these numbers are with high probability primes. You can also not use my naive algorithm because it just simply takes too long. What you might be able to do is to use these in combination. You could use first is prime to get something that was probably a prime, and then you could test more carefully with the naive algorithm that it was a prime. That would still take a long time because you have to do this quite a number of times, right? Because I have to make it all the way to 10 to the whatever it was, 30 or something like that. And so actually what Helfgott did in order to solve this problem was to use the fact that for numbers that are called Proth numbers, so these are numbers that have, we've actually encountered them before, they of the form k times 2 to the n plus 1, where k is an odd number that is a lot smaller than 2 to the n, then actually there's a primality test that works the other way. So it's also a random primality test, but it works the way that if it says that a number is a prime, then it is with mathematical certainty a prime. If it says that a number is composite, then with high probability it's composite. So the solution in that case is to use a different kind of test, which will tell you that something is in fact always a prime with mathematical certainty, and then use that. Even though it's less efficient, it sort of takes care of this problem. And then actually, as they explain in their paper, there's a few times where they couldn't use this test, but then they were down to like a handful of cases, and they could use a slow algorithm for this. So this is what you would have to do if you're in a situation where you need to know something with mathematical certainty rather than with high probability. Excuse me. So let me show you another instance of this. I'm not going to run it because it takes a long time, but we actually had a different situation which was parallel to this, where we were using floating point numbers, right? And up to now, I've talked about situations where we use pseudo-randomness in order to speed up computations. And then, most times it's fine for us to do something with high probability, but sometimes we want to know for sure mathematically. Also, very often we use approximations, we use floating point numbers, even though we know that this is not accurate, and most of the time we can live with that, right? So if we're just close enough to the numbers that we want to compute, then that's fine. But here's the situation where we actually want to know with certainty something about it, a number, and this is something that very often occurs when you have a number which is close to 0. Because if you have a number which is close to 0, you probably want to know with certainty that it's positive or negative. Right? It's very difficult to know with certainty that it is 0, but this interval arithmetic that came up in one of the other videos, you can use this to know for certain that you have a number, for instance, which is strictly positive. And this came up in Hazelgrove's analysis of the Polya problem. And there was this weird computation here that Hazelgrove did, and he found out that if he plugged in 800, the point was, could you find a number that you can plug in and get a positive number out, and he did this, right? So he got a number out which was roughly 0.005. But the question is, can we know this for sure? Right? And there's sort of two problems. We could have round-off errors in our computation, and actually also we have an imprecision because these numbers we've used in the computation were roots of the zeta numbers, roots of the zeta function on the critical line, of course, that were provided to us by Odlyzko's homepage, right? So I'm not questioning these numbers, but I only have them with a certain precision. So the question is, can I know for sure that I have a positive number? And yes, I can know this for sure because the interval arithmetic gives me that.